Our next session is on points, and this is a topic that's near and dear to my heart. Some of you may be old enough to remember there were 5 workshops of this size on just point rendering. And it comes and goes and comes and goes. And now that we have a billion triangles in a model, you got to wonder, why do I have to have this mesh? So I personally think we may have hit a turning point with some of the advancements that have been made lately on point rendering. That remains to be seen. We can set up proposition bets after this, but I'm gonna go on the record and say I think this is gonna start becoming a dominant topic again for years to come, and I am happy to wager. So our first speaker, please come up because we have agreed to sharing of duties.
Yeah.
So this is reducing the memory footprint of 3D Gaussian splatting. It comes out of George Hatakis' lab, who's been very hot lately on this topic. We're disappointed George is not here. Please complain to him. And the speaker is a new PhD student, so please introduce yourself to him. He's going to be a new member of our community for some time.
Yeah.
And his name is?
Panagiotis. Yeah.
Last name too.
Papadonakis.
Okay.
Yeah.
Thank you. I appreciate it.
Okay. So let's repeat that. So hello everybody. I'm Panagiotis. Oh wait. Sorry. Yeah. I'm Panagiotis Papadonakis, and today I will present you our work reducing the memory footprint of 3D Gaussian splatting. This is a joint work with my awesome colleagues, Yorgos, Bernard, Alexandre, and George. So just as a teaser, in this project we want to go from the video on the left to the video on the right. As you can see, they're pretty similar, so that's not very impressive. What if I told you that the left one comes from a representation that's 1.3 gigabytes and the other one is only 48 megabytes? I find that interesting, right? So let's get started. So the problem we're working on is novel view synthesis, in which, given a set of input images of a 3D scene, we want to build an algorithm that will allow us to render the scene from any point that we want. It's effectively allowing us to make this awesome free viewpoint navigation. So in the distant 2020, the field was completely revolutionized by NeRF, everybody probably knows, a way to represent 3D scenes as a continuous radix field. In essence, in this representation, each point in space has a color and density value, and you can find the color of a pixel of array by integrating this by computing the rendering equation, so computing this integral. Of course, in practice, you don't compute the full integral. You take discrete samples. The color and density of each one comes from a MLP. Then you render an image and compare it with the ground truth. And since all of this is differentiable, you can propagate the loss through the neural network so that it better represents the scene. We can see something here. So a lot of follow-up work has built upon this technique by improving the training or rendering speed. 2 notable works that I want to mention is MIPNER 360, which is that allowed for NTA-less representation of 3D 360 capture of unbounded scenes, and also InstantNGP that introduced a multi-resolution hash grid that feeds the MLP with local features so that we can have better training and rendering speed. Anyway, but the main point of NeRF representation is that the scene is represented by this MLP in an implicit way. So, in the not-so-distant August last year, the authors of 3D.js introduced a way to represent 3D scenes using 3D Gaussian kernels, which are splatted on the screen, using a very similar volumetric rendering equation, but instead of density, you have opacities. But anyway, it's pretty similar. So the main difference here is that the discrete samples that this rendering equation is evaluated on are explicit primitives, and more specifically, there are 3D Gaussians that have a specific shape, geometry, opacity, and color. So using a differentiable rasterizer, you can get the color of a pixel, render an image, and as before, since this rasterizer is differentiable, you can propagate the loss into the Gaussian's parameters directly. So an instance of the Gaussian splatting training can be seen here. So it converts. So if we were to make a coarse comparison between the two families of models, and I'm taking InstantGP here as an example, we can see that 3D Gaussian splatting has equal or better quality, especially if given more time to train than InstantGP. It has better training speed, again, for the same quality, and definitely has better rendering speed. But its main disadvantage is that the representation size it's too big. Usually it fares around 30 to 60 times bigger than its NERF counterparts. So making it extremely hard to store and transmit. Why is that though? So for NERF models, the representation comprises of the neural network itself, so just the weights, along with any auxiliary structures like the hash grid for InstantGP. In the contrary, because 3D-GS is an explicit representation, the memory comes from the per primitive memory footprint times the number of primitives that you have. So in our case, we have a lot of parameters per primitive that, as I said before, they describe the geometry, the opacity, and the color. And the number of points is determined by the initialization that you have and an adaptive control that was introduced in the original 3D-GS paper that tries to cover under and over reconstructed areas. A key difference between the two families is that for NERF models, the memory requirements are constant among scenes, as it is only dependent on the network architecture, while for 3D Gaussian splatting, it depends on the scene size, as you need to have the explicit primitives to cover to represent the geometry in the scene. So in this work, our goal is to reduce the representation size by introducing two techniques to tackle the problems of big number of points and the big memory footprint per point. And also we will try to store the representation more efficiently. The ultimate goal of this project is to have a representation that is with a size that is comparable to InstantGP or NERF in general, while without compromising the visual quality, of course. So moving on to the first technique, we observe that in many cases, either due to the optimizer converging to bad solutions or the adaptive control over-densifying some regions, there are a lot of points were clumped together, creating extremely dense regions. So in this video that I'm going to show you, I'm going to reduce the scale of Gaussian so that we can distinguish them more clearly. So I hope that plays. Yeah. So as you can see, we have some regions that are very densely reconstructed. I want to point out the skeleton of the bike, which is a textureless region that could be very well reconstructed by a handful of Gaussians. But as you can see, it has way too many of them. So we think that this has some redundancy. So we want to come up with a redundancy metric for our points that quantifies how redundant these points are, and then cal points that score high. The idea behind the redundancy metric is that after rendering, the scale of detail that we can represent is limited by the final representation. So, of course, for an image that is just 1 pixel. So we search the redundancy in the number of ellipsoids that fall inside a 3D region that gets splatted on the same pixel, as these ellipsoids will probably share information, and so they might be redundant. So to compute a redundancy metric, we initially need to find the 3D footprint of a pixel. Of course, since we have a perspective projection, this shape has this footprint has a trapezoidal shape that gets bigger the further away we are from the camera. In order to account for details seen at multiple scales, we choose the smallest possible size that, of course, comes from the closest camera you can see here. So yeah, for the points that lie in this red region, we would take the green size over the blue one. And now, having said that, we proceed in drawing a sphere of size equal to this 3D memory footprint of a pixel, centered at each primitive center. Then we calculate a redundant score for every region as the number of ellipsoids that intersect it. And finally, for our ellipsoids, we take the minimum redundant score out of the regions intersected. So probably that's too complex, so I want to walk you through an example, which doesn't appear very nicely, but anyway. So, I mean, you can see the screens maybe. So let's say that we want to find the redundant score for R2. Initially, we just draw the spherical regions based on the pixel size, pixel footprint that we saw before. So that could look like that. Then we want to find for each region how many ellipsoids intersected. So for R1 and R3, this number would be 2 because it's intersected by only 2 ellipsoids, while for the middle one, the R2, this number would be 3 because it's intersected by all 3 ellipsoids. So now for the R2, that is our main focus here, we would take, to calculate the redundancy metric for R2, we would need to take the minimum out of the regions intersected. So since the ellipsoid R2 intersects every region, we would take 2 and not 3. So basically, this we take this minimum because we want to be conservative in the redundancy metric calculation. The intuition behind that is that by taking the minimum is that we can have a point that lies in the middle of a redundant region or with a region with great redundancy, but due to its shape, it can contribute to a region that has a lower redundancy. So removing this point could be detrimental to that other region. So by using this criterion, we proceed into culling points that have a high redundant score, combining that with removing points that have low opacity, something that was introduced in the original Deblur-GS technique either way. We just do it a little bit more aggressively. We achieve 50 to 6% fewer points. I'll now proceed to the second method that takes care of the per primitive memory footprint. So just as a refresher, these are the parameters that each primitive has. So of these, the 14 on the top are deemed vital because they describe the position, the shape, the opacity in the RGB, and the color, which is necessary. It's essential for the volumetric rendering equation. So we're left with some the spherical harmonic coefficients. So for 3-band model, these coefficients are 45, and they amount to more than 76% of the total memory, and they're only used to model view-dependent effects. However, the specularities and non-diffuse materials of in our scenes take only a small part of the total scene, and also 3D Gaussian splatting can do some tricks to model specularities through other means, as is to have specular primitives inside objects or through the alpha blending process itself. So spherical harmonic seems like the obvious candidate if we want to limit the per primitive memory footprint. So our method consists of adjusting the spherical harmonics bands of each point following 2 observations. They're not vital, by the way. So it is possible that even though the spherical harmonics produce a color that varies greatly with the direction, we only observe it through angles that the evaluated color is very similar. It's more or less the same, as you can see here. Also, we want this observation to not be affected to be affected by the contribution that this point has to these views. So let's say that we had third camera in which the point has a low contribution because it may be masked behind other points, so the transmitter that reaches there is very small. Even though this gets a very different color compared to the other two, we wouldn't want to be affected by that. So to formulate that, we compute the average and the variance of the evaluated color of a primitive for all the training cameras, weighted by the primitive's transmittance, which accounts for the thing I told you about. So in that way, for primitives whose variance falls below a threshold, we proceed in replacing their base color, that is the RGB, by the weighted average, discarding the spherical harmonics bands and the associated parameters. So in this case, we would go from 48 parameters to just 3. Second, there can be cases where the additional spherical harmonics bands are aligned in such a way that the resulting color observed from specific views can be adequately modeled by the lower order band. And this is important because the more bands we use, the more coefficients we use. And actually, the number of coefficients per band increases as the band increases. So in a similar fashion as before, we proceed in calculating the color of a point with the full number of bands, then with every other band, I guess. And then we calculate the average distance between the two for all the training cameras. So we can proceed then for primitives whose color distance falls below a threshold, we can discard the higher order bands and just keep the lower ones. In that way, effectively, so for this example, we could discard the red one and just be left with a green one, effectively reducing the number of coefficients we require. So we apply these two methods once at the point where the densification stops, around the middle of the optimization, so that any information lost can be retrieved by the rest of it. Combined, they provide a drop of 97.5% in spherical harmonic memory, which amounts to 91% of total memory on the 3 data that we tested. Finally, I'll talk about the compression of the stored file. So that's very simple. We've noticed that the range of several parameters is very limited. The best example is opacity, which is just a number between 0 and 1. So we follow a very simple k-means clustering scheme in which you, instead of keeping a float for every parameter, you only need to keep k floats equal to the number of codebook entries, and then an index to that codebook for each parameter. Since the index is probably smaller than a full float, we benefit from the size difference. In our case, we use 20 codebooks of 256 entries each, so we only need to use 8-bit indices. The second observation is that apparently 3D Gaussian splatting is not very sensitive on float precision, so we can go on and replace the remaining float parameters with float 16. That's pretty simple. So that is the codebook entries and the positions, we use float 16. So we apply this compression scheme at the end as a post-processing step. Combine these two techniques offer a factor of 3.4 additional compression. So putting everything together, we see that we gain a reduction of about 27 times in size, while the BSNR drop is limited to 0.32 dB. Additionally, I want you to focus on this. I have corrected that anyway. Whatever, to the first line, to the point calling method, but now it's whatever. Anyway, so as you can see, so for the point calling, right? It's just the first row. The drop in quality is non-existent, basically. Not like you don't have a drop in quality, which strengthens and confirms our choice of criterion to cal points. Anyway, here we compare with InstantGP, MERF, and the original 3D-GS model. MERF is a streamable NERF model that renders at high frame rates. So we can see that our model achieves only worse quality than 3D-GS, while having memory that is comparable to InstantGP and way lower than MERF. Also, we can see that we achieve a higher frame rate just because we have a lower number of primitives that we need to render. Then moving on to the qualitative results, we can see that our method, again, retains the visual quality of 3D-GS, which is superior to that of InstantGP and MERF, as, yeah, there are no apparent differences between the baseline and our model. Finally, to highlight the difference in representation size, we've also provided a WebGL viewer that you can see here. which, the contrary to other viewers, we also implemented the view-dependent effects. Maybe you can see that on the bike. So to conclude, we introduced an efficient resolution-aware primitive pruning method that reduced the number of points during optimization. An adaptive spherical harmonics bands adjustment that greatly reduces the average per primitive footprint, and also a codebook-based compression and half-load quantization that compresses the final representation. All in all, in the dataset that we tested, we achieved a 27 times compression in memory, 1.7 greater rendering speed, with only a minor reduction in quality. So this is it. Thanks a lot for listening. And you can check our code, not our code yet. You can check our project page and WebGL viewer here. Yep. I forgot to update my slides anyway.
Thank you. Yes. Are there questions?
Hi. Thank you. This is great. I wonder if you can expand a little bit on the codebook compression, like how you achieved, how you arrived at that result, and what the ablation looked like, and what you found along the way.
Yeah, I mean, the ablation wasn't that thorough, maybe. So basically, you have different. I thought that you have different families of parameters. So you have. Of course, we don't use for position, but you have, for example, 3 scales, one opacity value, some per channel spherical harmonics bands and stuff. So we just proceeded into creating a codebook for each one. We found out that 256, which was the original goal because it's just 8 bits, 256 entries were enough. So yeah, we stayed with that. Probably, so right now we do, let's say, each parameter has a different index to the codebook. So our k-means clustering is single-dimensional, unidimensional. So yeah, someone could maybe try to compress even more by taking the full RGB, like the full vector, as one index to some other codebook. But yeah, we didn't do that. Okay.
We have time for one more question.
Okay, so maybe I'll ask a quick question. So this amazing work, there is so much like follow-up papers for Gaussian splats that it's very hard to catch up. Like every week there are a few of those. It gives me a lot of stress, and all of them are amazing. And my question is how this approach of adaptive culling, how it would compare to some other approaches. So few folks have been trying, for example, to include the notion of MIP mapping to Gaussian splats for anti-aliasing, etc. And also there is more recent branch of work where people, for example, first train a nerf, then they throw out nerf, and they use it for populating the splat positions, which seems to give like very nice placement, much better than structure from motion. So my question is about something that I don't have a good intuition. Like, do you think that this approach of adaptive culling, it's like redundant if one was to use those other approaches, or it can be used complementarily?
Yeah. So first of all, as I've said in the beginning, the main issue that you have big points in the first place is that the initial point cloud is very sparse, and you want to densify it to create more points. And that densification procedure is a bit doesn't work very well in every case. So the first step, I guess, is to just improve it or change it altogether, do it from scratch and do it in another way that works nicely. So there has been a lot of work that try to, as you said, place points and spawn points in a different way. So distillation is something, but I mean, it works very well, but I don't like the fact that you have something that you need to train as well, and then you distill it into your framework. There's a nice work about probabilistic spawning of points, so that's interesting. But yeah, we wanted to, let's say, be as less intrusive as possible in the original framework and try to do something with that. So yeah, but after that, maybe trying to delete points based on our criterion can work. But I'm not exactly sure because we've tested it with the current densification technique.
Okay, let's thank our speaker again. Our next speaker is Market Chitz, who's a postdoc. And we discussed being a postdoc is the best stage of career because you have no administrative responsibilities, you're well-trained, you just do work. And he's going to be discussing LOD work on this. As we all know, LODs are often the most critical part of a system, and it's a problem that's strangely intractable in almost all systems. So it's the thing that will always be with us as graphics changes.
1 second.
That and getting the PowerPoint slides to load. That will also always be with us.
Google Slides. Okay. Where's that? Just 1 second. Stuck. Okay.
Thank you.
Yeah, hello everyone. We've been working on simultaneous LOD generation and rendering, and basically our goal that we're trying to reach here is to be able to instantly view large point clouds without pre-processing. Because if you have large point clouds right now, it can take minutes to hours to days to pre-process into an LOD structure before you're actually able to view it in real time. So what we're doing here is we create the LOD structure on the fly to do that while loading the data. So here's an example with a point cloud with 680 million points, 11 gigabytes of data, and you can just drag and drop this into the application. And let me play it again. Into the application, and the method works fast enough so that all of that finishes in 1.4 seconds. And the LOD structure is generated on the fly during this 1.4 seconds. And the way that we're doing this is we do an incremental LOD construction directly in CUDA. So we stream the points from disk to GPU memory, and in each frame we insert about 1 to 20 million points into the octree. The number kind of depends on how fast we're actually able to stream from SSD, and we have let's say 30 threads that stream the points to disk to GPU. In some frames we've loaded 0 new points, in other frames we've loaded 20 or maybe even 30 million points. And in order to keep real-time frame rates at all time, we have some kind of time budget, let's say 10 milliseconds, and we keep inserting new points into this octree until we reach the time budget, and then we stop and render the intermediate results. And the remaining points are then added in the next frame. The LOD data structure that we're generating is not a new one, so we're just generating existing structures, just much faster and incremental on the GPU. And the structure is very similar to the layered point cloud structure, or even more similar to the octree structure by Wand et al. And what it looks like is we have inner nodes, so lower levels of detail, that are represented by voxels with a grid size of 128. And we have leaf nodes with the original full precision point data. And because the voxel data is very sparse, we don't store them in grids. We instead store them in lists and basically treat them like vertex buffers. And the leaf nodes, they have up to 50,000 points. And if more points are inserted into a leaf node, we then split it to get finer grained leaf nodes. Here is what the rendering looks like to the left, and to the right, the octree structure. So here you can see the geometry colored by the octree node they belong to. And we're always trying to strive for pixel-sized voxels, so you're not going to see any boxes or anything. It basically looks the same as if you'd render all the points instead of replacing them by lower resolution voxels. So for this slide here, I'd like to highlight two main problems. There's more details in the paper, but there are two main problems. And one of the problems is that we're dynamically inserting new points and voxels into the octree nodes over time. And the other problem is that we have 10,000 CUDA cores that we have to keep in sync with operations like splitting a node, expanding the octree, actually inserting the geometry into buffers. And the two solutions that we're using here is, first we use a linked list of chunks of points as a dynamically growing structure. And we use iterative deepening as some kind of approach where you can expand the octree and keep lots of threads in sync. So the linked list, it contains, so each of these chunks here contains 1,000 points or 1,000 voxels. And in our implementation, yes, in our implementation it's 1,000. Can be smaller, can be larger, and basically then makes a trade-off between wasted memory and construction speed. As you can see here, the last chunk in each of these linked lists here might have some empty space. And with a chunk size of 1,000, we usually had only about a waste of about 1-3% of memory, so that's not much. With smaller chunks, there's less memory waste, but 1-3% doesn't matter much anymore, but the octree construction time would increase. With larger chunks, octree construction time decreases, but there are very diminishing returns, so 1,000 is quite fine. Also, because we have 1,000 points, consecutive points in memory, we essentially have coalesced geometry. And what that means is that we get a good rendering performance. Because when a block of CUDA threads or a warp of threads tries to render consecutive points, it can just load them from the block in one go and not do some kind of pointer tracing or anything that you'd usually have with linked lists. During the parallel octree construction, we insert batches of points with up to 1 million points. Basically, we're loading batches of points from 1 million points from disk, stream them directly like that to the GPU, and then if we insert 20 million points in a frame, we insert 20 times 1 million points. And this is also the place where we can just stop inserting new points if our time budget exceeds the current frame. We have to expand the octree if we are adding more than 50,000 points into one of the leaf nodes, and we have to keep 10,000 or more CUDA cores in sync. And we do this with this 4-pass approach here. And the first pass is that we expand the octree by one level at a time, and we repeat doing expansion until no more expansion is needed, so until the leaf nodes are smaller than 50,000 points. In the second pass, we then create the voxels for the inner nodes. So while traversing through the inner nodes, new voxels are created and then later on inserted into the octree, but not yet. In the third pass, we allocate memory for the new geometry because the first and the second pass, they don't actually insert into the octree nodes yet because we don't have the memory yet. But once we've done that, so in the third pass, we now know how much memory we need, so we can now allocate enough chunks for that. And then in the fourth pass, we actually insert the new geometry into the respective octree nodes. So here an example of that. So let's assume we're not adding 1 million points. Let's just add 10 million points into this octree here. And each leaf node has a limit of 5 points. So what we do is during the expansion pass, the first pass is repeatedly count and split until no more splitting is necessary. So we traverse the 10 points through the octree to the leaf nodes. We count how many points there are in the leaf nodes afterwards, and we can see, okay, 10 points, that's too much. We have a limit of 5, so we have to split this leaf node here. Then we do the counting again, and we can see there's still one leaf node here that's too big, so we have to split this one again. And now we can see there's no more splitting necessary. All the leaf nodes are fine-grained enough for the new points, so the octree expansion is finished. Then, in the next step here, we sample the voxels. That means we take these 10 points we're inserting into the octree, traverse them through the octree again, but only through the inner nodes. And whenever a point hits an empty voxel cell in a node, we create a new voxel here with the point's color, and we store this new voxel into a backlog buffer. We cannot directly insert it into octree yet because we don't have that memory. But here in the third pass, we now have the sufficient memory. So we can now allocate, so we now know how much memory we need. So we can now allocate the chunks, link them together, and then in the fourth pass, we now take the points again, traverse them again. So we do lots of traversal here, but traversal is really cheap. So we traverse them again to the leaf node. Now we can actually insert the points into these chunks here. And then we take the voxels that we previously generated and actually insert them into the respective inner nodes of the octree. So that's pretty much it for the octree construction. We just repeat this until all of the points are inserted. There's some more details that you can look up in the paper, but these are the most important steps here. So let's have a look at the results. This point cloud here is a photogrammetry scan from Marrow. It has about 680 million points, takes up 11 gigabytes of disk space, and the throughput for this approach is about 505 million points per second here. And this includes the time from loading the first point from disk until inserting the final point into the octree on GPU. And 505 million points per second, that's about 8 gigabytes per second. So you can utilize quite fast SSDs with this approach here. So here another scan. It's a very different scan. There's different point ordering, also a higher depth complexity because you have multiple floors here in this construction site. It's almost 800 million points, about 12.7 gigabytes. And with the original ordering, we can process this at a rate of 340 million points per second. This original ordering kind of means that the points are inserted in the octree more or less all over the place because of the way they were scanned during with the terrestrial laser scanner. We wanted to check what happens if we have a better locality by ordering them by Morton order. And yeah, if you have a good locality, then the throughput would rise to 580 million points per second. So here, video again for the Marrow point cloud, where we have this 680 million points. Takes just about 1.35 seconds until all of that is loaded and the octree structure is generated on the fly. So here you can see what happens when you look around here. A little bit of frustum culling, and yeah, and if you adjust the LOD, you can see that we have this pixel-sized voxels here, so not rendering any boxes. Yeah. So in any case, we've shown that this works fast. So if you can stream points from disk very fast, the method can keep up. But it's even more interesting for use cases where loading the points is slow. And this happens very frequently for aerial LiDAR data, for example, or many other kinds of point clouds, which are stored in the industry standard compression format LIC. And with 100% CPU usage, we were able to load the points at a rate of 30 million points per second. And here it can take quite a while, so half a minute for smaller point clouds, minutes to hours, until you actually go through all of these points here. And with this method here, you're able to look at results right away. Only problem right now, limitations, is that the method is in-core. So the largest point cloud we were able to process was 800 million points. Yeah, and it's only targeted to points. So as future work, we'd of course like to expand this to triangles and splats as well. And also do some anti-aliasing for inner nodes, because right now the voxel colors are initialized by the first point that hits that voxel cell. Would be much better if you produce an average, and even better a view-dependent average, because at very low levels of detail, you will have large voxels that contain geometry that's originally pointing in multiple directions. And yeah, we would need different colors based on directions. And one of our largest priorities here is to make this work with arbitrary large data sets. So for example, there's a point cloud from the Netherlands with 640 billion points, or from the United States with 60 trillion points. And eventually we'd like to be able to just drag and drop that and instantly view stuff. And I believe this is possible because for an overview viewpoint, so we initialize an overview viewpoint, and we just take a random sample of 1 million points. And it doesn't matter if you have a billion or a trillion points, loading a random sample of 1 million points is a constant time. And from there, you can navigate through the scene and keep loading geometry from the disk and inserting it into octree based on the user's current viewpoint. So yeah, this is what we're currently working on. But yeah, in conclusion, we've shown that we can incrementally create these LOD structures basically as fast as we can stream the data from disk. and then render results right away. So we have enough performance left to render the same results in the results in the same frame. And we've also shown that rendering linked lists of chunks is fast because each of these individual chunks has qualist geometry. And if you render that in a compute-based pipeline, then the threads just load 128 consecutive points, render that, the next 128 points, render that. And at some point, they might have to jump to the next chunk here, but that's also pretty much a no-op. So yeah, with that, thank you for your attention. And if you're interested in trying it out, you can get the source code from this GitHub repository. Just make sure you're actually trying it with a fast SSD, because this project is really targeted towards actually being able to utilize fast SSDs. Thanks.
Thank you. That's the first time I've seen 1 trillion points in a slide. Should get a medal. We have time for questions.
Thank you for the talk. Great overview. I have two questions. One on, I assume you're using some form of CUDA to graphics interop so that you don't have to copy the memory back. Can you speak a little bit about that?
Yes, we are using OpenGL for the graphics. And basically, OpenGL is really just there so that we can populate the frame buffer and display it. Everything else, including the rendering, is done in CUDA.
And so are you doing the, I assume you're passing points from CUDA just as a buffer to OpenGL, and then OpenGL is doing the rasterization, correct?
No, the rasterization is also done by CUDA.
Okay, got it. Second question, I'm curious because CUDA, of course, you need an NVIDIA GPU. Have you explored using compute shaders using Vulkan or even Web GPU now?
Yes, but this paper here is basically the reason why I started CUDA in the first place, because I tried OpenGL computers, I tried Vulkan, but it's probably possible, but it's not fun. So with CUDA, this was kind of the difference between horrible and comparatively easy.
Yeah, thank you.
Oh, I have a question then. So in your last slides, you were talking about like future work, like trillions and billions, right? And then you can sample 1 million points to start it.
Mm-hmm.
But you're still dependent on what you're loading from the disk. If you cannot sample 1 million points from the whole data set, right? You still have to wait until you load everything. So you're sampling 1 million points from whatever you can load, I don't know, in a second or so.
So we've been running the numbers and doing some tests here. And this compressed data sets, every 15,000 point is uncompressed. So we can basically already do a subsample of every 50,000 point. And we checked the SSD. So my SSD is able to load 1.5 million 4 kilobyte sectors per second. So basically we can do a subsample of 1.5 million points per second.
Yeah, what I mean is that you're dependent on what are the first 1 million points that you load. So you cannot like sample the whole data set.
It's a uniform random sample over the whole memory. We could do that.
Okay, makes sense.
Time for one more question.
Yes, yes. Thanks for the talk. I like that in that slide that you had the comparison between the two different orderings. So since I don't know exactly how fast generating the mortar ordering is, so can you tell me something more about it? So how fast is it?
So let me first start by saying that it actually doesn't make sense to combine this with first sorting by Morton order, because by the time we would have sorted, we would have already created LOD structure. We just wanted to check if it is faster with points with good locality in memory. Other than that, Morton order, you can sort this with integer sorting algorithms, and I think CUP should be able to. I haven't tried it. I just saw some numbers, and please someone correct me if I'm wrong. I saw something about 10 billion entries per second should be possible in theory.
Okay, thanks.
Thank our speaker again. Our next speaker is actually not an author of the paper.
Yeah.
Yet. He's agreed to stand in for the authors, so I've never had a lab mate that good. So let's give a little applause for the hero that we needed right now. And this is on any of us that have done point-based stuff. Sometimes the data sucks, and we throw it away normally. And this paper is, actually, we can deal with the bad data. So, please.
Okay, so hello everyone, and I'm Ziteng Liu. I'm not on the author list, and I'm not the author, so I'll present their work. Okay. So basically, the work is about solving the novel view synthesis problem in Gaussian 3D Gaussian splatting way, but with the camera motion considered. So let's recap on novel view synthesis. Recovering 3D scene information from 2D images has long been a persistent challenge in the fields of computer vision and computer graphics. So novel view synthesis is a process that creates image from source images and their camera poses, which involves generating image of a scene from a specific point of view when the only available information is pictures taken from the limited point of view, as I described here. Okay, so let's jump into the nerve. The emergence of neural radiance field has completely revolutionized the field of novel view synthesis. Since NeRF learns an implicit neural scene representations that utilize an MLP to map the 3D coordinates and the view-dependent color and densities through the differentiable volume rendering. Okay, so these are the pipelines of NeRF. I believe that you guys are already very familiar. Okay, so however, the neural network-based radiance fields entail high computational cost and substantial storage needs. Yeah. So 3D Gaussian splatting enables real-time rendering of novel views by its pure explicit representation and the novel differentiable point-based splatting rasterizer. Okay. So to achieve a high-quality radiance field, in ideal, you would need a clear input from camera. But however, in reality, you may not be able to retrieve such high-quality data. Factors like camera jitter or shutter time will often result in a motion blurring within the dataset. So in cases where input images are blurred, the reconstruction results suffer from blurriness and artifacts as described here. Okay, so therefore they proposed the Deblur-GS method for reconstructing 3D Gaussian points to create a sharp radiance field from a camera motion blurred image dataset. Okay, so since it's a 3D GS-based radiance field-based approach, so using the input camera view of the dataset, they can achieve the blur for that image. And when using the novel camera view, and you can generate the clear synthetic result of such views from such camera views. Okay, so before going over their method, I will briefly go over the related works. And a traditional way of solving the camera blurring problem is to do 2D image deblurring first, and then do the radiance field reconstruction and the novel view synthesis. Okay, so this has a problem, yeah, because due to the absence of the 3D information during the deblurring process, the preprocessed methods usually fail to generate satisfied results because they can't align properly between such views. So another piece of work arises that is based on neural radiance field. So reconstructing accurate neural radiance fields using blurry input images has been actively researched by the NeRF community. Deblur-NeRF introduced an end-to-end framework that jointly estimates the pixel-wise spatial varying blur kernel that's here the canonical kernel, and the latent sharp radiance field as here the NeRF MLP case. However, the blur kernel relies on the training of the deep neural network without geometry and appearance consistently in 3D scene representation. As you can see from the pipeline here, there are no geometry or appearance consistency considered, just the size of the kernel and the shift of the kernel centers. Okay, so another workaround that is a better NeRF bundle adjustment that uses a bundle adjustment technique introduced in another NeRF paper called BARF. Okay, so band NeRF models camera motion blur as a camera motion trajectory estimation problem, and hence requiring camera pose estimation method like bundle adjusting NeRF. Okay, so judging from the related work, previous work have some limitations. For the traditional image deblurring preprocessing methods, lack of multi-view consistency will bring artifacts and blurriness to the reconstruction result. And for NeRF deblurring, achieving high performance and accuracy remains a challenge. Okay, so here jumps to their method. And here's the pipeline of the method. Okay. Since it's a 3D Gaussian splatting method, the pipeline follows the framework of what the 3D-GS does. And what's different is that they now have a keyframe, a series of keyframe poses that describes the motion of a camera, and which can also represent the global rigid transform of all the Gaussian points. Okay, and this will be discussed in later slides. And by summing up the all the different keyframes and sample from them, and you got a time series of images, and using the stock 3D-GS rasterizer, and you get the time sampled series of images here, and you blend it, and you get the blurred result, and you take a loss to the target image, and you optimize the loss, and you do back propagation. Okay, and you solve this problem simultaneously. Using your camera and as the parameter of your overall pipeline. Okay. So first introduce the camera motion blurring model in this problem. The motion blur is a common manifestation of a camera shake that occurs when the camera shutter speed is too slow to maintain a stable camera pose. So the mathematical modeling of this process is integrating sharp image results during shutter time. In practice, the uniformly sample n time step within the shutter time as keyframe. However, that weight is optimizable if needed. Okay, and the blurred result will be approximated by the accumulation of the this sequentially rendering the rendered sharp results. Okay. So now that we have a series of clear images, and we need to model the camera motion trajectory, and since the camera can move in an arbitrary but smooth trajectory during shutter time, so they parameterize the camera pose in Lie group and approximate the camera trajectory with a linear cubic spline or K-order Bezier curve. For the linear case, this works in the most time. For most cases, there are two control points, and it's very useful for modeling shutter time and the relatively small amplitude of camera motion. And it's optimized very fast, but it's with limited expression ability. So within this model, they transform the global pose TT will be expressed like this, okay? And for cubic spline interpolation, however, 4 control points are required to represent the camera trajectory, where B here is the basis function of the spline, okay? And also the k-order Bézier curve. As we raise the order higher, the expressiveness grows. And it's useful for extremely blurry input images. And the precise performance depending on tuning the parameter k, okay? So now that I've introduced their camera model and the trajectory, let's go to the scene optimization process. So the total loss can be written as a combination of L1 loss and the SSIM loss using the parameter lambda. And in addition to optimizing the 3D Gaussian scene parameter theta, it's also necessary to jointly optimize the control point post T of the camera trajectory. And as you can see here are the derivatives calculated. And in order to optimize the post parameters of the camera trajectory control points, they need to calculate the gradient with respect to the camera pose. Okay, so by this deduction, the gradient can be decomposed into 3 terms. One is the color term related to Gaussian point encoding. The other is a covariance term related to Gaussian covariance that controls the shape, and the position term related to point cloud position, which is M here. And through experiments and analysis, in order to improve the accuracy, robustness, and computation efficiency of the calculation results, they chose to omit the color term and the covariance term like this, and only return the position term. So in this setting, transforming the camera pose is equivalent to transforming the position of the Gaussian points. So instead of optimizing the camera pose directly, they optimize for global transformation for all Gaussian points per camera. This approach allows to pass the pre-transformed Gaussian points position to the Gaussian differentiable renderer without any modification. So you can just use the stock 3D-GS informations, okay? So using automatic differentiation to propagate the point cloud position gradient calculated by the renderer to the global transformation, thereby improving computation efficiency and minimizing development costs. And here jumps to the results and the discussions, okay? So the data set used within the evaluations is taken from XBLURF. It provides a synthetic and real data set. And the synthetic data sets derived from Deblur-GS and was synthesized using Blender with more challenging motion blurry. And the real data set is captured by the dual camera system, where one camera captures a single blurry image with a long exposure time, and the other capture a sequence of sharp images during the exposure time of the blurry image. So here are the quantitative comparison of novel view synthesis on the real data set. They show that the method consistently outperforms previous approaches on image deblurring and novel view synthesis. The first 2 group is for the 2D image deblurring preprocess method. One is called the Restomer and another called the NavNet. And after the preprocessing, they use 3D Gaussian splatting reconstruction and do the novel view synthesis and get a result. For the 2D image. For the 2D image methods present here, they struggle to generate the deblurred results due to the absence of the 3D scene information during the deblurring process. And as for the bad nerve, they fail to reconstruct the scene due to instability and insufficient training iterations. As you can see, the Deblur-GS as a Gaussian splatting method, iterate can converges more fast than the nerve-based methods. And on the other hand, their method produces sharper results than the other two methods in the same training iteration. So here are the qualitative results of the different methods given by each group. Here we can see single image deblurring methods fail to restore the sharp image and bring artifacts but blurry images in Gaussian scene reconstruction. That is the third and the fourth column. And with the help of 3D Gaussian scene representation, their method can converge faster and produce sharper image results than Deblur-NeRF and XBlurF. And here are a demo video of their method. Well, can it play? Okay. You can see how shaky the camera is. Okay, so they also examine the efficiency of their methods in terms of memory cost. They observe that their method consumes significantly less memory compared to other methods. Due to the potency and representation capability of 3D Gaussian, they can efficiently represent their scene using an acceptable number of Gaussian points and minimal parameters, as opposed to employing a full-fledged neural network with a large number of parameters. Note that the 3D Gaussian splatting method can achieve higher frame rate in real-time rendering during inference, which is also a challenge for neural network-based radiance field methods. Okay, they also evaluate the effect of the representation of camera motion trajectory within the shutter time. They chose pole and wine scenes from XBlurF, which represent low-level and high-level motion blur, to evaluate image deblurring quantitatives respectively. And the results as shown here, as we can see from the low-level motion blur scene, the pool, which has a less shaky camera. The camera only has a small movements within the camera exposure, therefore, the linear interpolation is enough. And the quality is close to the higher order curve. However, for the high-level motion blur scene, for example, the wine scene, the camera may move fast within camera exposure, and the motion trajectory could be complex. At this time, the simple curve interpolation might not just be enough. So the higher order Bezier curves came into play and showed the better results compared to the other two methods. And note that the higher order curve requires more control points, which means more keyframe samples and the learnable parameters are needed. So therefore, the training time will be longer. That's a trade-off here. And therefore, their conclusion is to choose different trajectory modeling strategies based on the blurriness level of the input images to achieve a balance between performance and quality. And also, the reconstruction equality shows a gradual improvement accompanied by a consistent decline in the standard deviation as the number of keyframe increases until reaching a point of stabilization. However, the inclusion for more keyframes require rendering additional intermediate results during the training process, exerting a significant influence on training performance. So to enhance training performance without compromising reconstruction quality, they conducted this experiment first, and to select the default number of keyframes to 31 for their all the experiments they present here. Okay, and here goes the future work. And in this paper, they only considered motion blur from camera movement, and the camera can cast motion blur which is global, and the object can move too. So handle the motion blur caused by the object movement is it's a goal for them to do as well, and here as 3D Gaussian, not 3G. Okay, and they can also integrate the focus deblur, which is better models the camera and the actual characteristics of camera. Okay, and also one of the future work would be to combine with the co-map-free Gaussian method, since the existing initialization are derived from structure from motion, and if they are co-map-free, then the entire optimization will be more integrated. And at last, their vision is to extend to the reconstruction from multi-view to video stream, since video stream also suffer from such problem during movement. And okay, so this is their work. And if you have any questions, ask, and Wenbo will answer using the Zoom. Yeah.
So hopefully we'll have the office of the paper here on Zoom. Hopefully I'll learn to use the mic by the end of the session. There we go.
So Wenbo, can you hear us?
Yes. Can you guys hear me?
Yeah.
We do hear you.
Yeah, okay.
Do we have any questions?
Check. Go. Nice. Hi. Thank you. Great paper. So I'm wondering about at the end of the keyframe, like the keyframe slide, there was a drop after you reached a certain amount of keyframes. And so I'm wondering what's going on there. I have my hypothesis is this thing is actually learning a prior on the motion of the scene, and then too many keyframes are actually introducing noise. Do you have any observations on this, and how you can actually work to like make a prior so you don't need that many keyframes?
The number of the keyframe I choose is based on the experiment. Like the last experiment shows that when you have 30 keyframes, you may have the good result. And I didn't design the automatic way to find the best number of keyframes. Yeah.
Thanks.
So it basically based on experiment. Yeah. Like you do a lot of experiment and find the best parameter.
More questions? I have one question. In the future work, it said if the motion blur comes from objects, and I'm wondering what's the correct answer for that? Is it a moving object that's still blurry because it is moving, or is it a particular time that you isolate from that motion?
The motion object often relate to the dynamic Gaussian, like you want to reconstruction the dynamic scene, like a dancing people, or a moving car. And when the car moving, they may cause some motion blur, right? And I want to reconstruction the dynamic scene, and the car is still clear, like it's not motion blur, something like that.
Thank you. We have time for one more question, if there is one. Okay, let's thank our speaker again and the author of papers. Our final talk before lunch is from Ben Watson, And you'll notice there's a new set of words in this title that we haven't seen yet called light field display. And I've worked with Ben many times over the years, and he's always been ahead on displays. And when we first started working together, he was doing crazy talk about 10 million pixels, high resolution, high dynamic range. And now you can buy that at Best Buy. And light field displays, if you haven't seen them, are really amazing devices. And again, we can start some proposition bets on will we have these, but extrapolating from Ben's former predictions, I think it's a pretty good bet.
Thanks, Pete. Right, so again, my name's Ben Watson. I'm presenting work of my recently former student, Ajinkya Gavani, who just started a job, so couldn't make it today. Talking about rendering for light field displays. So this is a light field display. It essentially provides 3D effect as you move around in front of this display. It offers you different views. Many of these displays today will work with multiple viewers, so it works for a little crowd gathered in front of the display. And what we're working on here and what I'm presenting is rendering for these things. The way, without going into all the gory details, the way these things work is by putting a lens array on top of a very traditional display, and then introducing a trade-off between spatial and angular view resolution. So as you move around, these lenses ensure that you're mostly going to see the correct pair of views for your two eyes, as long as you arrange all the views correctly under the lens. And so the fundamental problem for a rendering person is making a whole bunch of views now, not just one, whole bunch of views real fast, in real time. And the standard multi-pass way of doing this, for this particular display we had with 48 views, you have to, it takes 33 milliseconds. So just jumping right into our results. So we're doing this with almost the same quality, sometimes better, sometimes worse. For this particular view of a gallery scene, 1.7 times faster. For this Sponza scene, 3 times faster. For this coconut model, 2.5 almost times faster. And for this car, 8 times faster. So in the rest of this talk, we'll briefly touch on prior work. So we built directly on some of our work that we did last year, presented here, and a few years earlier. And then we'll talk about the highlight techniques from this paper, and then look at a lot of results and discuss. So this technique builds on some work in 2017 by my former student, Adam Mars. Essentially what it did was, its core innovation was, let's make point clouds just in time, frame by frame, specialized to the particular needs of this particular frame. And the way we do that, let's see if I can, maybe I can't point. All right, the way we do that is by turning the rasterizer into a point generator. And so the geometry shader becomes basically a setup engine that for every triangle decides how we're going to sample it. Then we create points with the rasterizer. Fragment shader puts things into a buffer, and then the compute shader renders out all these multiple views in parallel. So we were working on shadows on this paper. Last year we presented at this conference work that improved on that prior work with efficiencies in rendering in sampling rate. So in particular, we constrained rendering to only sample enough to serve the eyes view and not the needs of the supposed resolution needs of any off-screen buffer. And then also we found out that you can defer shading even more when you have all these off-screen buffers. So these pictures over on the lower right here show how many pixels in these off-screen buffers. In this case, we were working on reflections and environment mapping. How many of those are actually shaded? So even much less. That was a real efficiency as well. All right, moving on to this paper. Okay. Well, you can sort of get the idea here. Maybe you can see the rest of the little pixels on the monitors, but the basic way that these displays work, as I mentioned earlier, was that they introduce a trade-off between spatial and angular resolution. So sacrifice some resolution across the screen in order to provide more angular views to produce that 3D effect. And so in the end, what this does is change the aspect ratio of each view, right? Because in some way, you're giving up resolution across the screen, spatial resolution, to achieve more views. And then what that means then, too, is that you no longer typically have square pixels in effect. So exploiting this fact, we, in this paper, describe how to sample to match the effective view resolution of each view buffer. We also observe that often you are rendering based on information in a number of textures, and if the resolution in those textures is for a particular view coarser than the resolution that the pixels in that view, then there's no need to spend a lot of extra time sampling the same texel over and over. So we sort of constrain resolution, the resolution with which we generate points in that sense as well. So we introduce an additional constraint on sampling, point sampling. And then lastly, those previous two methods were focused on achieving higher speed. This method is focused on maintaining quality. So as I mentioned earlier, the way that we render lots of views at the same time is in the compute shader. And in the compute shader, we don't have access to a hardware mapping functionality. And so that's a real limitation in quality. So what we describe here is what we call multi-view mapping. Essentially, at a very high level, what we do is, as we're setting up each triangle for sampling and turning into points, we determine the highest and lowest rate at which any texture out there will sample it. And that gives us overall views. You can see on the left here an LOD map for a kind of LOD map for mapping, a minimum one. And then on the right, we have a maximal one. So that becomes basic input for more specific point-by-point LOD determination based on the particular configuration of each view. We interpolate between those minima and maxima, figure out what the right color from the texture is based on that interpolated LOD, and then render. And so here on the left, you can see the interpolated LOD map for a particular view, not all views. And then on the right, the more traditional view-specific version of a LOD map done traditionally. And this does produce a real improvement in quality. These are two error visualizations. On the left, there's a lot of green. So in this HDR VDP3 error differencing map, green means more error. But on the right, after we use our mapping technique, the differences are, the error is much reduced. So all of this gets combined. I won't walk through all the gory details here, but all of this stuff gets combined across a version of the same pipeline I showed you in the related work. The two earlier techniques are in red and green, and then the stuff I was talking about is in blue. Most of the sampling efficiencies are happening in setup during the geometry shader, and then the mapping technology or method that I was talking about is spread across the geometry shader, fragment shader, and compute shader. At the end here is something I haven't talked about yet. We're making lots of views, but obviously you're not showing them all individually or separately under the lens on the display, and so you have to interweave them and in something called an elemental image array, and so that's at the final post process you see on the far right. All right, so let's look at some results. So overall, I think you can see first that not a lot of difference between these images. I should say that these images are what we call behind the lens images. So in contrast to what I showed you at the beginning of the talk, where we were taking pictures through the lens, here we're looking at what the display beneath the lens is actually showing. And so it's all interwoven at this point. So at the top, in the Sponza scene, most of the stuff that you're looking at is further away. So the view doesn't make a big difference. Things aren't that blurry. But on the bottom in the gallery scene, more blur because things are closer to the eye. The other thing to see here is the speed. So you can see that on the left column, that's the ideal, very high resolution, very anti-alias slow rendering that we're comparing to for error. And then standard multi-pass straight ahead rendering approach takes about 30 milliseconds. And then you can see that we're faster with very similar quality in the right two columns. And then we can do anti-aliasing, now not just across space, but also across between views, which we think, and I'll talk a little more about this later, could be very valuable for this sort of rendering application. But you can see here that we hit a bandwidth limit. So even though our quality is similar, at this point now we're slower than the comparable multi-pass render. We're rendering here on a fairly modest RTX 3070 GPU, and there was a step that occurred when we sampled that much. Here what we're doing, by the way, the reason it's slowed down is because we're doing super sampling, so twice as many samples across space and between views. And then here we're beginning to zoom in. So this is all the Sponza scene. The top row shows the one of these interwoven behind the lens images. And then the bottom two rows are one particular view extracted out of that. And so then on the left is the standard, and the next two columns to the right of the leftmost standard view are multipass, and then the right two columns are our method. And you can see that in many cases we have less error. So in particular, wherever you see for the MVR column some green or yellow, and we don't see it for us, we're doing better. But there are a few cases where we're a little bit worse. Here's the gallery scene, same layout, and you can see that overall we're similar in error. There's one exception, I think, right here on the lower right in the single view error image. There's some error in the back, and that turns out to be not because of our technique so much, but because in compute we were running into some precision issues. So at the back, it's there, and we're not. We think we could fix that with a little more systems engineering. Here we're super sampling, and you can see that error went away, and the quality is very similar to a standard multipass technique. And here we are in the gallery. Okay, now let's discuss briefly. All right, so this technique is faster than multipass but similar quality. How does it depend on the content? So it slows a little bit when there's very high resolution textures, in particular when they're higher than the resolution of each view. We spend a lot of time working on those, but there's an overhead with the min mapping in that case. And then as you saw, when we want to do a lot of sampling, so there are lots of pixels or lots of super sampling, in particular across space, the technique slows down because it makes more points to cover all those pixels. And then lastly, interestingly, the method stays quite fast if you're just interpolating between views, because you can use the same set of points as you did that you've already generated by and large. So minimal cost, lots of extra images. So we think that could be really important. As I mentioned, one of the problems with light field displays is something called crosstalk. So when your eye is sort of on the boundary between two optical views in front of the display, your physical eye, you'll see parts of both of two images in that eye. That's crosstalk, and that doesn't look good. And so in that case, it would be nice to have some kind of anti-aliasing, right? It's view aliasing is what's going on. And so we think that could be particularly valuable. We need to, as I mentioned here, test the view supersampling with some human observers and find out how beneficial that is. How much does that reduce the sensation of crosstalk? And obviously, we need to try this technique with a better GPU, see if it continues to scale as we believe it will. Did I leave something out? No. And then lastly, one of the things that we did here that I think has a lot of potential is that where previously a lot of these point rendering techniques that I covered that this is based on were about generating not very visible off-screen views. Here, all the stuff we were doing, all the points we were generating, were ending up right on the screen. And so that opens up the possibility of applying it in many other areas, perhaps for foveation or for depth of field effects. So I'll stop there and take any questions if you have any.
Thank you.
Sure.
There's some questions.
I have a quick question.
Yes.
So first of all, thank you for the talk. I loved it. So I'm curious, have you done any calculations on how big of a display would you have to have for you to be able to tell the difference between something rendered with your method and the traditional method?
How big would it have to be? I'm not sure that if we were rendering at the resolution a certain display would require, that you would be able to tell the difference just by that, right? So it would slow, right? The bigger your display, the more points you need to adequately sample for that display. So things would get slower, but I think the quality would stay more or less the same.
So the quality is like independent of how big your display would be?
Well, the quality is not really independent, so you have to do more work the more pixels that are on a display, right? Just like you would with a ray tracer, right?
Got it.
Yeah.
Thank you.
Sure.
So I have another question.
Yes.
I hope you don't mind if I ask sort of a more practical question, but have you found, what do you think might be the best sort of use of this technology, including light field itself? Is it scientific viz? Is it gaming?
Oh, well.
Is there a real niche for this?
Well, I mean, you can already, I didn't mention, but you can already buy these displays.
Yes.
So Asus and Acer are putting out laptops and monitors with that.
Oh, attached to laptops already. Okay.
Yeah. Mm-hmm. I'll say, though, that to improve quality and speed, many of these are a sort of a slightly different version of light field displays. So they track your eye position and very, in a sort of makes sense. They're only going to render the views that your eyeball needs, not all the other views, right? So that means that it really only works for one person at a time. But that's fine for like a laptop, I think.
Yeah.
Yeah.
Oh, and one more comment. If anyone hasn't seen this in real life, there's a small one over in the cesium reception area on the shelves. It's a looking glass device. It's the only device that's plugged in over on the award shelves over there.
So let me to follow up your practicality question. One thing I always wow my students with in class is that just imagine that there's a big display like this or at a movie theater. One of the challenges of going to the movies is good seat, bad seat problem, right? So if even in the movies, the camera's in a certain position, and ideally you want your eye to be as close as relative to the projection as the camera's eye position.
Sure.
And if you could figure out a way to record movies in a light field-like fashion with many views at the same time, there would be no bad seat, right? Wherever you sat, you would see the right thing. And then there would be an additional bonus if you went back to the movie and you sat on the other side of the cinema. You could see part of the movie you didn't get to see before.
You can see the bad guy hiding out of frame. That's great. Thank you.
We have time for another question. Okay, I'm going to ask it. I'm going to channel this morning's speaker. So you're using a primitive the GPU wasn't designed for.
Yes.
And a screen the GPU wasn't designed for.
Yes.
If you could build your own hardware, could you do this for like 10 watts instead of 400 watts? Or is like the bus bandwidth the real issue?
Well, I'm not a hardware expert.
Yeah, neither was this morning's speaker.
Yeah.
Okay.
I'm becoming one.
We
and
all are.
I'm becoming more of a believer in specialized hardware. I think that we've sort of gotten spoiled by the GPU. We're used to it's become a general purpose processor, not a graphics processor. And so it just works, we feed it more watts, it goes fast enough, we're happy. But I think we should get back to our roots and start building things that better serve a particular application. So in particular, one of my soapboxes is rendering and display should start merging, I think. They shouldn't be separate anymore. Modularity is great, but it has its limits. So I can talk more about that maybe tonight at dinner if you want.
That is a good segue to lunch, because that's a pretty profound statement.
All right.
Thank you.
Thank you.